you'll hear us talk a lot about edge machine learning because we think that's a um, really important trend that's happening across all industries, but in particular for digital health, it has huge implications of what we can achieve, what we can do with data and algorithms that are really exciting. And so in today's webinar, I'm going to go and talk about at a very high level, what is this technology? What is Edge ML? What does it mean? Why is it happening? We're going to dive into some customer case studies, so real applications of this in real products and what kind of success we've seen so far and the learnings we've had. I'll dive into how edge machine learning can be useful for you, right? What kinds of applications does this enable? What kinds of sensors can we work with? A little bit about the silicon technology, kind of what kind of hardware does it take to run this stuff? And then I'm going to dive right into like how I've seen this play out to be successful, going right from clinical health data collection all the way through to machine learning algorithms, and of course, the insights that we can derive from those. And then I'll do a little bit of demonstration too, and how some of this looks like when we're working with the tools needed to achieve this. And then of course, Q&A, ask me anything about what I presented here or things that you've been wondering about in the digital health space. So what is edge machine learning? Sometimes we talk about embedded machine learning. This is a new trend where we've been able to achieve a lot of advancement in both machine learning algorithmic technology, so the math that we use to train an algorithm and then have that algorithm mimic some expert knowledge. That's really what machine learning is. Some experts said that when these sensors do this, this is happening, right? Someone's breathed in, right? And now their oxygen levels increased. What we're doing is we're training a very complex math equation to approximate what that expert would see, or that maybe golden medical device would show. And we're trying to do it as cheaply as possible using off-the-shelf sensors. So those advancements in machine learning are enabling us to do much more, a lot more cheaply in real hardware. At the same time, new processor capabilities, so smaller silicon that's lower power. We have accelerators that are now at our disposal for under $1, plus new types of sensors, right? Sensor technology is getting better and better. Like I showed an Aura Ring here, which I'll talk about a little bit about, what we can do now with PPG is really amazing. And so edge machine learning is when we take that machine learning, we match it with sensors, and we try to process that data with the machine learning as close to the source as possible. I'll talk about why in a second. It could be on the device. It could be in the app that's connected to the device over Bluetooth. It could be in a local gateway. It could even sometimes be at the edge of the cloud, if that makes sense, right? If you have data coming from lots of different users distributed around the globe that you need to combine together to run your algorithm, it might belong at the edge of the cloud. And we can work on an amazing range of sensor data. So the kind of sources that we work with day in and day out with our users include motion, right? 3-axis accelerometers, magnetometers, PPG, ECG, EEG, skin conductance, computer vision, right? We're dealing with a lot of computer vision systems, both worn computer vision, as well as external computer vision, for example, in a space, right? And sound. Sound has a lot of really interesting applications for breathing sounds, other sounds that people make related to their health. And we can do this with just about any sensor you can imagine. If it produces numbers, we could probably process it with machine learning. So this is what Edge ML is. And what's happening across all these industries, and in particular in digital health, is that there's several things that are driving this trend of machine learning into these health and medical devices. So innovation's one, right? Being able to drive new algorithms to your customers much faster. This is becoming more and more important, and this is a data-driven game, right? You need the data sets to be able to do this, and machine learning helps you take advantage of that data. Privacy is a big deal, especially in health, right? We're dealing with very sensitive information from users, some of which are consumers, some of which are patients. Edge machine learning helps us deal with this because the data really stays on the device. It doesn't have to go anywhere for us to get that insight. Power, right? The ability to go process something locally actually saves us a lot of power, because these days the biggest hog of power is the wireless technology we have to use to move data around. That's much more expensive, an order of magnitude more than the silicon used to just do local processing. Cost, right? When we can do this locally, we can save the amount of money we need for storage and compute by sending tons of data to the cloud. That is getting expensive. Your AWS bill really is an issue in many, many organizations. And then, of course, reliability, right? We don't need all that bandwidth and latency. We don't need the internet at all for this stuff to work. That's one of the beauties of machine learning, is once you've done all the complex engineering, the data set collection, the engineering of the ML algorithm, when we put that thing on a device, it just works, right? You throw data in, you get the answer out. And that will work even with low or no connectivity environments. So lots of these trends together are moving this machine learning technology to the edge. And in the case of digital health, that means two devices are very close to devices. We have a lot of experience working with health wearables and health applications. I'm going to go through a few of these and just talk about some of the kinds of algorithms people work on, and some of our learnings from doing that. Aura is one. We've published a case study recently on Aura. Sleep tracking and algorithms related to sleep and activity are the big thing that Aura is really, really good at. And we have some great results from machine learning derived sleep algorithms. Slate Safety makes specialized equipment for workers and firefighters. And so for them, we worked on a really interesting heat exhaustion algorithm. So detecting heat exhaustion ahead of time, right? So 5 to 10 minutes ahead of onset as a big deal for firefighters, for example. And so look at the data we use to do that. And then more recently, No Labs, really interesting company doing non-invasive glucose monitoring with very new types of sensors, really cutting edge technology, having to scale up to do clinical studies. First, talking about Aura, I'm sure many of you know what Aura is, but if you don't, I'll explain. So I'm wearing an Aura ring here. I use this personally to help my sleep. So Aura has a very interesting I'd call it a low-key wearable device, in the sense that it doesn't buzz, it doesn't beep, it doesn't have an interface. It just tells you how you're doing. And so what Aura does is they use a combination of motion, PPG, skin temperature, all the sensors it has on board to give you insight about your sleep and what's called your readiness. And for Aura, right, working with all that sensor data combined with all the different reference medical device data that you need to do these clinical studies was a real challenge, right? Wearing multiple rings, PSG sleep setups, multiple SpO2 sensors, external motion sensors, all at the same time. And doing that, going from, doing one night of sleep is one thing, going to 10 and then 100 and then thousands of nights of sleep is a very big data problem, and it's a very messy sensor data problem. And so what we've done is helped create the infrastructure, all the tooling to be able to process all that data directly from the field, so directly from sleep studies and other kinds of clinical studies, and make that data useful for the scientists creating new algorithms. And in this case, we had a couple things that happened. One, we brought down algorithm development time from years to months. It used to take these algorithms many years to develop, and they were quite brittle, to being a data-driven approach where we could do this in a matter of months for completely new algorithms. And this new data also allowed us to get better levels of accuracy. So best-in-class sleep algorithm scoring, and better accuracies in that compared to other devices. And so really, really amazing results from the Aura team, and Aura continues to do absolutely incredible work in the space of data-driven algorithms. I think their team is one of the best. Other case I talked about was Slate Safety. So Slate Safety's device measures body temperature on the device. It measures activity, so motion in the device. And from that, we're able to look at also heart rate, of course. We're able to combine that all together and look at their historical data for future core body temperature. Because when they have existing, this is one of the cases where their device had already the kind of interesting data they were looking for. Then we see this sometimes. Oftentimes you need additional third-party devices to verify this, but their device is already looking at core body temperature. What we wanted to tell was, what is this body temperature like how can we predict it 5 to 10 minutes out in the future? So actually they had the labels that we're looking for. So we're able to use data sets that they collected in our back end and help them in a very short amount of time. This just took a couple weeks to do an initial kind of proof of concept, to use that data to develop an algorithm, combines all of the sensor data together to estimate that core body temperature 5 to 10 minutes out. And they give a warning to a fire chief and the firefighter when they need to reduce their exertion, get out of the heat zone, right? Because they have a risk of damaging their body permanently. And so this gives you an idea what some of that data looks like. So one window of that sensor data, and then what that data looks like as a whole. It's really interesting to see how these regression models in particular, what that data looks like in these kind of tooling for machine learning. What else can you do with machine learning and sensors and health algorithms? Well, the sky's the limit, right? These are some of the things that we're seeing very commonly, leading use cases, eating and drinking behavior, both for life quality as well as for elderly care, many different types of stress detection, including cognitive fatigue, which is a big deal in, for example, pilots, sleep quality detection, like talked about with Aura, activity classification, performance improvements and performance metrics, heat exhaustion that we talked about. Classifying human tasks is very tightly related to health use cases. So what gestures are people using? What words are people speaking, right? Can be very useful. Do we need to process someone's language as they're talking? Deeper into the health space, fall detection, preventative illness detection, non-invasive measurements, like we talked about non-invasive glucose. Post-procedure recovery is a really interesting case for health providers as well as insurance companies. And then, of course, in pharma, trial monitoring. So when we have people taking experimental drugs, how are they actually doing, right? What kind of improvements or non-improvements are we seeing, and not just having them check in from time to time. So lots of interesting use cases, and we know of companies doing much, much more than this. Anything that can be done with sensors and data really is on the table here. Well, what does it take to create these algorithms? Well, that's going to spend the rest of this lunch and learn on, kind of my experience and what we've had to do to go and make this happen. Well, first thing is data, right? Really, this all starts with the data. And so to get to the kind of algorithms that you can start to commercialize, we usually need to start with one subject or a very small handful of subjects. Start with the sensors that we can get a hold of. These could be sensors that are in off-the-shelf hardware that you can buy. So many of these algorithms are built over the top. You can use existing sensor devices, combine them together in a solution, or they might be sensors that you're integrating and building in new hardware. We take those sensors, we're combining them with this small number of subjects to create kind of initial test algorithms, kind of rapid testing to understand what's possible. When we see promising results from that, we then need to pretty quickly scale that out to 10, 20 subjects, getting a larger data set that covers the target audience or target patient audience that we're looking for. And then we need to scale that to hundreds and then to thousands, and in some cases even tens of thousands of subjects in order to get the kind of general purpose algorithm that we can deploy to a whole population of consumers or patients. So that scaling from a few to tens and hundreds and thousands, That is extremely hard to do, and to do that and operate those clinical data collection studies at scale. We then need to continuously improve those algorithms. So these algorithms are not about, oh, we're going to suddenly build a 1,000-person data set, and then we're going to create this ideal algorithm all at once, and then we're going to put it into production and forget about it. That is not how ML algorithm development works. It really works in very small increments. We start with one data capture from one person. We start with a small number of sensors, and then we get a very early indication of, can this data even be used to derive an algorithm? And then we look for the data that we're missing in order to improve that algorithm, the sensors that we're missing. And this starts from day one all the way through to production. And then post-production, we have to keep maintaining this. And then finally, we need to speed up this innovation cycle. So once we are able to create an algorithm, we have this infrastructure set up, it's important that we're then helping teams to do more, right? Derive new algorithms from data sets that already exist. So oftentimes we want to collect a little bit more data than we need, because it could be useful to develop new algorithms on that, or go back and start new data collection campaigns in parallel to what we're already doing. So we see customers that start with 1 or 2 algorithms, and they can pretty quickly scale up to 5, 10, 15 new campaigns in parallel. So really speeds up innovation around data and health ML algorithms. Now, what does that mean in practice? So we'll dive in a little bit deeper into the stages and technologies involved to go build these algorithms. And I'll show a little bit of a demonstration as well. So this is a high-level architecture of what it means to go build these data sets and this initial algorithms. And I won't show all the deployment stages here, just kind of that simplified, hey, we're going to deploy this to a device or close to a device. But this really, the big part of this starts on the left with the data. And when we talk about clinical data collection for health algorithms, this often involves 1 or more of these wearable devices. It could be your own or an off-the-shelf device combined together with the subjects that we're measuring, together with clinical reference devices. So we'll oftentimes have people hooked up with ECG sensors that we trust, EEG sensors that we trust, and these should be health professional trusted devices, because this is the golden data that we're comparing to. Could be oxygen, could be glucose, could be motion, you name it, stress indicators, whatever it is you're looking for that you want to, in practice, replicate with the cheaper wearable devices. We're going to measure those things in parallel. And then we oftentimes have the researchers or the medical professionals involved running these studies. They're part of this as well. We have to combine all that data together in what we call data pipelines. So there's a lot of automated pipeline work that needs to be done. Sometimes we're gathering these files from the field with like upload portals that we generate securely. Sometimes they're coming through backend infrastructures through AWS or Azure, and that we're collecting that data together. We then have to align and validate data. So I'll show an example of that, but a lot of work we do is in aligning all that sensor data together so it is accurately time synced. And that's really important. If we have something telling us that, all right, we entered a deep sleep stage, we need the data coming from the wearable device, those sensor data like PPG, to be really accurately aligned with the sleep study sensors and the score that we got from the sleep practitioner. That all has to line up. Otherwise, we're going to have the wrong labels at the wrong time with the wrong sensor data, and that's going to hurt our accuracy. So lots of work goes into aligning all that data, validating it, checking the quality, and then putting it into data sets that can really be used at scale, right? Whether they're 1 to 2 or 3 people or tens of thousands of people in that data set, we need to be able to use that for real science. The second part of this is then that continuous model development. And I'll show you what that looks like, but it involves feature extraction, so the low-level signal processing we do to take the useful pieces. Sometimes we're combining multiple sensors together, even from multiple devices. The machine learning algorithms themselves, so what we train to detect something that we're looking for, a sleep stage, an analyte level, a particular activity we're looking for. And then we need to test and tune these algorithms. So this is not just about machine learning, it's also about applying the algorithm to work for the cases we have. So we might be trying to improve or reduce the number of false positives, reduce the number of false negatives. There's different outcomes we have that we can trade off in these algorithms. So we need tools to be able to do that. And then finally, after we've deployed, it doesn't stop there, right? We need to monitor how these algorithms are doing in the real world. And then that's a source of new data. So this is where we have this performance monitoring and new data trigger coming in. Oftentimes we'll get additional data set when we see that something works differently than what we thought, right? We have a consumer that says they're doing this activity, right? Whereas our algorithm said they're doing this activity. We asked them, are they sure? We can use that as new data into our data set. So a lot of data and machine learning, kind of continuous machine learning infrastructure that goes into these things. What do some of these algorithms looks like? Well, this is a cognitive fatigue algorithm that we recently looked at, combining PPG, IMUs, temperature, some feature engineering from that to derive additional subsets of values that we're looking for, or derivatives from this. So HRV, HR, exertion, respiratory rate, sleep quality or sleep stages, and then pushing that into a combined machine learning powered cognitive fatigue estimator. So this is something that we may want to build, looking at that outcome that we're looking for. Now, there's phases involved in this too. This doesn't happen all at the same time. Typically, we'll have a data collection phase, followed by some feature engineering, algorithm development testing, and there's a little bit of a feedback loop here. We'll go back and do more data collection step by step. But one safe way to think about this is, for the most ambitious stuff these days with proper tooling, we can do less than 6 months of data collection, less than 6 months of algorithm development. And in some cases, it can be, this entire process can go down to a few months if we have a well-oiled machine and team really knows what they're doing. We've got access to data easily. We've got access to all the devices. We could do this quickly as well. But this is kind of a safe process for development. And finally, a little bit of looking at what this looks like in practice. Data correlation and error catching is really important. So this is a great example of where we do checks on data coming in and we automate that. So some of the checks we might do are, are the device data present looking correctly? Do we have the ECG and EEG files? Is the reference data starting within the right time? Does it match the time zone we want? Does the correlation work? And in this case, this is an example of where we found an error where the correlation was not working, right? The times were off by I don't remember what the time was in this second case, but tens of seconds, which is a problem. We can detect that kind of thing and then make sure that we fix it, because this could destroy a data set, right? Really important. We're investing sometimes millions of dollars in data sets. We've got to make sure that the data is high quality and correct. Yeah, here you can visualize what this looks like, right? When you get this kind of desync between different sensor inputs. So for example, your wearable and a reference device, this is the kind of thing we can set up automated checks for. And that could save us millions of dollars, literally millions of dollars that we may waste. Doing data collection where the data quality is poor could have, really horrific impact on potential algorithms we can generate. Data discovery becomes very important. So this is an example of how we are generating graphical representations of what our data sets look like. This is already before we do machine learning. And so these are different states of stress, right? Amusement, meditation in a stress state. And so we can visualize what this data looks like, but we can also start to look at feature importance, which is really interesting in the early stages of this. What of our features are important? We might sometimes generate 60 or 70 different features that could be interesting in a potential health algorithm, but probably not all of those have a equal impact on the machine learning performance. So we start looking at what kind of impact would these have. We might even drop features that are not useful that could have a big savings in energy and other overhead for such an algorithm. So data discovery and visualization is really important as you're working on this type of algorithm. And then finally, algorithm develop itself has to be a team exercise, right? We oftentimes hear about people doing algorithm development on their own. Oh, we have the super data scientist that just does it in isolation, but these things really aren't in isolation, right? These are teams of several to 10, 20 people working together, from the data collection end all the way through to deployment. We have to be able to host all the pieces of algorithms because it's not just about machine learning. We have a lot of things happening in data pre-processing. There's a lot of feature extraction work that we're doing before we ever get to a machine learning classifier. And so hosting that and being able to visualize it's really important. In this case, this is an algorithm that goes and does this kind of stress detection using acceleration, ECG, EMG, chest temperature, respiration, and then in parallel, we do some interesting things with chest movement. And Mike, I just want to check, do I have time to dive into a little bit of a live demo as well?
I think you do. Let's see, it's 10:32 right now. This is slated to go for another 13 minutes.
Great.
So yeah.
I'll just do that real quickly. I don't want to dive into our Q&A time too much, but just to show another example of a kind of algorithm that we have people working on all the time in digital health. This is a case of data coming from about 4.5 hours of data on running, sitting, and walking, measuring 3-axis accelerometer, PPG, and then using a polar heart rate sensor in parallel to that. And we combine all of that sensor data together with the labels of what was happening at that time into a data set, and something we can collect directly from all these sensors. Put this into a data set. Those labels are important because that's what we want to determine from the sensors. We want to know, is somebody walking or is somebody running based on these sensors? So this is what the data set kind of looks like. We can do this kind of data explorer work where we can see how this data looks like from a machine learning algorithm point of view. Like if we push this data into an algorithm, does it cluster together? And this is really interesting. We actually see that, yes, it does. This kind of pretty nicely turns into green, orange, and blue clusters. They don't have to be perfect. Machine learning is pretty smart to set this stuff apart. And sometimes here we might have mislabeled data. So this, for example, this is a great way to catch mislabeled data. This is probably not sitting. It's very likely running, and it may just be mislabeled. It's at least this particular window, or it could be that there's a quality problem here, right? This person might have been running, right, instead of sitting in this window of this data. So it's a great way to check quality in your data as well. We then map out these kind of algorithms. So the technique that we use is breaking these down into understandable, pretty simple blocks of algorithm. We don't try to put this into one massive magical algorithm that nobody understands. We really try to break it down that we understand each step of this. And that includes windowing, window increases, frequency adjustments. We then do multiple types of data feature extraction and signal processing. So in this case, we're going to do a PPG to HR conversion, and that could include additional HR, HRV, IVI derivatives. In this particular case, we kept it simple. We didn't do that. And then another block to do spectral analysis on accelerometers, because accelerometer processing is very different than PPG processing. And then we can then combine those two things together into an ML classifier that then tells us how this works. And we like a lot of visualization, so we can visualize, what PPG peaks look like in each of these windows of data, and then we can look what this accelerometer data looks like and all the output values from that. And that turns into a machine learning algorithm. So we can then train a real machine learning algorithm. In this case, this is a pretty early stage of algorithm development. We can already achieve almost 94% accuracy. We could get a lot better through data quality and additional data. but it's a great start early in the project to get to that point. So just a few things of kind of like what this kind of process looks like to be able to derive and work on this kind of algorithm with modern tools. Yeah, and then finally, I'd welcome anybody who wants to do this type of thing to our community. We are a very powerful machine learning platform at Edge Impulse, and what we're trying to do is enable scientists, domain experts, device makers to go be able to do this kind of engineering work. And we're doing that already at pretty massive scale, right? Already over 100,000 ML algorithms like this created by people around the world. And we work with the leading brands on their very specific AI algorithms. Yeah, and then finally, we have a big conference coming. It's going to be exciting. It's called Edge Impulse Imagine. This is the second year we're doing this at the end of September. Really focused on the use cases for the technology, right? What kind of things can we go solve using machine learning and these edge devices? And so great example of a speaker this year from the digital health space, Caitlin, really well-known founder of a startup called Clue, and then an executive at Medtronic, is going to be talking to us about how digital health and machine learning are coming together and all the exciting opportunities and applications in this space. So please do sign up for Imagine and please join us. You can join virtually and listen to everything happening at the event. Yeah, and finally, happy to take any Q&A questions.
Very nice, Zach. So yeah, just a reminder to everybody that's watching right now, the chat window is now enabled, although it did zap Zach's slideshow for a second there. So you guys feel free to throw any questions in there that you may have for Zach, or click that raise hand button. That's right. It's directly at the middle bottom of the screen. And we have 2 raised hands already. Sheba Ibrahim, let's see, you should be able to enable your microphone as well. That's all activated. You can go ahead and jump on in.
Okay, good afternoon, everybody.
Hey, good afternoon.
So it's really awesome. I'm really grateful for this webinar. I'm actually connecting from Africa, Nigeria specifically.
Welcome.
And thank you so much. So I've been working on a project, and I think I came across Edge Impulse last year. And one of the projects I've been working on of recent was using IoT and some of the data gotten from IoT to actually solve some of the climate issues we're actually facing here in northern Nigeria, because we're facing serious desertification problems. But from the aspects of health, 2 years ago, I actually worked on a project, and basically, I just used a couple of sensors that were actually available. And from this webinar, I think I really want to dive back to that project, but I really need some insights again, because I think I had a couple of errors initially. And with TinyML coming into play today, it's really awesome, because now I don't really have to send my data. Normally, I usually use TeamSpeak or AWS to send my data for my ML analysis, but now I can actually do some of those ML algorithms at the edge. But is it possible for me to be able to actually run most of the predictive analysis from the microcontroller, which means every single thing, I don't necessarily have to send most of the data to the cloud platform?
That's a good question. I didn't get a chance to talk too much about the levels of silicon technology, but a really good kind of rule of thumb is that if it's sensors, 95% sure it'll fit in a microcontroller. You might have to adjust those microcontrollers a little bit from the kind of size of it, but almost all sensor applications will fit in a microcontroller. And so you might need a bit more flash and RAM, you might need to upgrade your microcontroller somewhat, but that's the kind of class of compute. Audio will also usually work in a microcontroller unless you're going to NLP. So if you're just looking for audio sound patterns, that is microcontroller compatible too. And then when you get to computer vision, it could go either way. We'd have some classes of computer vision that work in MCUs, and some classes in computer vision that would require an MPU, something Linux-based, in order to process it. So I hope that helps, but absolutely. And then Shiba, our forum is great. So we have a lot of great developers on our forum. Please go do ask there if you run into problems. You've got other people that have probably solved them before.
Thank you so much, Zach Shelby. I really appreciate it.
And we had Owen next with a question.
Hey, Zach, this is a really good conversation. So some of the questions, we are actually 4 of us in the room. One of the questions that we were thinking about was actually along the lines what Shiba asked is, if you want to eventually port algorithms down to the hardware level, could you essentially do reduced form implementations of those in such a way as to get individual sentiment back from individual users that then somehow filters back to the larger models that you have developed, say, on the cloud?
Ah, got you. So that's a very advanced question. I'll try to keep it simple. What you're talking about is kind of active learning is the general subset. So what that means is that you've got a model in production, and I had a slide about that here. You got a model in production, and what's happening is that most of the time that model will work fine, right? But sometimes you'll see that your model is failing. And that's good, actually. That's an opportunity to collect a new data sample and push that back to your data set. And yes, that can be done. We do have the ability to do things like active learning today. So actively push new data samples. And they can be really small, right? You might just be looking for one very small piece of interesting new data that you don't have. Push that back in your data set. But then, because we're dealing with health algorithms, usually you want to keep the scientists in the loop on that. So you don't just blindly take in that new data, right? You analyze it, you look at, is it really what it looks like it is? Right? What are we seeing here? Then you go and, like, let's say once a month, right? You go spin a new version of your algorithm, push it out to your devices through an over-the-air update. And then you look at how you're doing after that. There are techniques like federated learning, but federated learning is very, very difficult. There's few organizations in the world that can really deploy it. Google's one of the only. But what federated learning does is it lets you kind of retrain or update those models in the field, but the problem is really only works for human-in-the-loop applications because you don't know what those labels are, and you don't know if they're even correct clinically. So that gets us, that's like kind of an opening a bag of worms that we actually don't know what we've trained and why it works or doesn't work. So I prefer more of a scientist in the loop kind of model.
Right. Yeah, no, I totally agree. And I think for us, the challenge is that we are a class 3 medical device company. So the quality engineering that's associated, the documentation and the testing that we have to do in hardware to make sure that this goes out into the field is a long process for us.
Super critical, yep. So you need to be able to document everything, including where did the data come from, who verified it. That's something I didn't even start talking about here. But yeah, that verification of every piece of data, signing it, knowing where it came from, auditing it, super important in that process. We had some other questions here on the chat as well. Can these algorithms go through FDA approval? Very good question. So I was just talking with Caitlin about that the other day, and Caitlin came from Medtronic, where they've worked on this problem at scale for a long time. And the way I think about this right now is if you are monitoring and measuring human health, and that can be, of course, that can be on the consumer side where you're good, and this can be in the medical space as well, we have a much easier time with the FDA. If we are making health decisions, medical decisions directly, or actuating, right? We're injecting insulin, for example, as a result of doing an ML algorithm. This is where the FDA is not all that clear yet. They say that, oh yes, we're open-minded to using ML, but nobody knows what that means, and we don't quite know how to get through the process. So this is where the kind of it's still fuzzy. Now, I believe we're going to get there, but it's much harder. And Owen just mentioned class 3 devices, right? It's much trickier than to get through the process. So I wouldn't say it's black and white. I'd say it's a whole spectrum of where is it appropriate today to use machine learning, and where it will be in the future. But I do think we will get to the point where, with the right methodologies and the right the right frameworks, we will be able to use machine learning in most FDA applications in the future. Do we have any thoughts on use cases for digital smell sensors? Oh, really interesting. That's a good question. So we have had a lot of, I haven't worked on we have had some commercial cases, but we've seen a lot of people in our community starting to use these VOC sensors with microcontrollers to do smell. I've heard of some medical applications and health applications. You're looking at, for example, sicknesses based on smell, including things like COVID based on smell. Super interesting. We've also had people doing things like differentiating between different types of Highland Scotch using VOC sensors. So these sensors can be very accurate in the sense that they can tell very small differences between things. I think the trick is validating that. And again, the clinical data set collection is the hard thing. But yes, we are seeing VOCs become more and more interesting. And those are microcontroller compatible, totally. You can do it very, very low power. Where to learn more, I would look at the Artificial Nose project at EdgeMPulse. We've got a developer who's published that. So there's lots of good instructions on how to write. I actually think Mike wrote the article on that originally around the artificial nose. Another question, I'm starting to work on a project for epileptic seizure detection for on-device inference and learning how to do it as a C++ library. What are your advice for collecting data, considering ethics in the process, even if it's synthetic data? Oh, really interesting question. Well, I mean, somewhat this is going to depend on where you are in the world. I mean, obviously you're going to have to work under an IRB, would be recommended. So one thing you probably want to do here is look for a research partner. So if you're doing this more independently, look for a university or a research hospital that you could do this with to use their guidelines for ethical data collection. That would be my strongest recommendation, is kind of follow the scientific norm for doing data collection. On the seizure, right, the tricky thing will be you're going to need to validate seizure, right? At the same time this is happening, you don't want something that you might confuse with seizure. It could destroy your data set. And then, of course, you're going to have opt-in with patients' privacy issues. So you're going to have to deal with anonymity, which I didn't talk about here, but it can be dealt with, but you have to deal with anonymity for those patients as well. So a bunch of issues to deal with, but it's not all that different than any other data collection dealing with patients, right? And dealing with health. You're gonna have to deal with the same things. Just because you're doing ML, it doesn't change it that much. Is it possible to have two standalone inference models on the same device? From Sharmila. Also a great question. Yes, of course it is. There are some technical challenges with SDKs and libraries that call the same thing, so sometimes it's hard. What we recommend right now is if you're running on Linux, it's no problem. You're running different threads with these things running, they don't interfere. If you're running on a microcontroller and running an RTOS, it gets harder. Then we recommend going multi-core, also because of the processing load. So with multi-core MCUs, you can do that today. And then finally from Stefan, regarding feature engineering, is it mostly done manually? Do you automate this? Very good question. So I'd say it's like engineer assisted. Think about it that way, is how this feature engineering works. So if I look at this and I go into these feature blocks, so all these feature extraction blocks, these are reusable blocks that we have in libraries. So we actually have whole libraries of different spectral features, PPG, dealing with IMUs, dealing with audio spectrograms, all kinds of out-of-the-box things that just work. And you literally just click them together and start using them. So most of these, some of them don't have much configuration, so there might be a little bit of low band, high band config that you need to tweak. In the case of spectral features, the block's quite advanced, so there's a whole bunch of things you could tweak. Choosing the right values can be hard, so what we do is we start applying what's called AutoML. So we have something called EM Tuner that does let you kind of automate the process of finding the right combinations of algorithms and then the right ML algorithm architecture. So think of it as like a advanced hyperparameter search all the way down to the sensor level. And so that does include the DSP feature extraction. What this won't do, though, is it won't go, we can explore neural network architectures, but it will not go create like a whole new class of feature extraction for you. If you need to do that, let's say you have an exotic sensor, then you need to go in and implement that new feature extraction. And we allow you to do that. So we can go and run this auto process that will suggest stuff for existing ones. And then we also have the ability here, if you go down to add a block, we have the ability to go add a custom block to this. You can actually implement a completely custom feature extraction block, and then you can deploy that in Edge Impulse and use it yourself. And so we haven't been doing wavelet stuff. I've heard a lot about it. It's interesting, but you could very well implement a wavelet block here and then start applying it with machine learning. It's not too hard to do. You write some Python and then you write some C++. I want to thank everybody for joining. Really always exciting to talk about all the stuff we've been working on. I really enjoy this space. I think we're changing people's health for the better, and we're using very interesting technology to do that. As always happy to chat with folks. Please reach out to us if there's some way we can help. And then do attend Imagine. We're going to have additional talks in this space and much deeper into the technology. And for developer questions, ping our forum or hit us at hello@edgeimpulse.com, and we're happy to help out. And thank you all.